Good morning, good evening, or good afternoon, depending on where you are when you're watching this talk here. So my name is Håkan Silfvernagel, and today I'm going to be talking about why you should consider WebAssembly in your next front-end project. So this is the agenda for today. First, we will look into what is WebAssembly, and then we will go through what does a hello world in WebAssembly, what does that look like? And we'll also look into how can we use Rust in order to compile a program down to WebAssembly. And we have some examples, like a game of life example that we're going to go through. And we're also going to discuss a little bit more about performance, about some real-world examples, what are the future plans for WebAssembly, and look into other frameworks that are using WebAssembly. And we get into a section that I've called New Old. And then we draw some conclusions. And finally, I have some references for those of you who would like to look into this a little bit further on. But before we start, I'm just going to give you some background information about me. So my background is I've been working with process automation and robotics. And right now I'm working as a manager for AI and big data at a Norwegian consultancy company called Miles. And my educational background is master's in electrical engineering and also a master's degree in behavior science. I'm also quite involved in the local user community here in Oslo, so I'm part of the Norwegian .NET user group. I'm also part of Oslo AI, and I'm a Microsoft AI MVP. And now, as of 2021, I've started an online AI school together with Eve Pardy called AI42. So I'm going to give you a little bit more information about that at the very end of my presentation. And if you want to get in contact with me, you can reach me on these following social media. And if you have any questions during my talk, you can either put them into the WebEx chat or into the Slack chat. So, first of all here, what is WebAssembly? So there was a group formed in 2015 consisting of all the major web browser vendors. And in 2017, the first draft of a WebAssembly was released. And in 2018, it was a W3C public draft that was published. And what this means for us is that we can use WebAssembly in any of the major browsers, Firefox or Chrome or Safari or Internet Explorer or Edge. And we can both use them on the desktop version, but also on the mobile version. So if we take a high-level view of JavaScript and WebAssembly, we can say that JavaScript is, as we know, a high-level language. It's very flexible and expressive, and it's dynamically typed. You don't need to compile, and it has a huge ecosystem of NPM packages and other things that you can use. Whereas WebAssembly is a low-level assembly-like language. We will quite soon have a look at what it looks like. And it has a compact binary format, and it has near-native performance. And the way that you use WebAssembly is you use a high-level language like C or C++ or Rust or Go, and then you compile down this high-level language down to the WebAssembly format. So this example is taken from a blog series by Link Clark that you can have a look at on this link here. But basically what it tries to illustrate here is that regularly, or usually what you have is that you have a high-level language, like C or C++, and then compilers will take this high-level language and then will translate it to an intermediate representation. And then another part of the compiler will compile it down to the target architecture. So in this case, either x86 architecture or ARM architecture. But now with WebAssembly, what we have here is we have a situation where we have code that will be executed over the web, and we don't really know on which target architecture will it run on. So WebAssembly is a machine language for a conceptual machine. So we can say that we have WebAssembly instructions, we can also call them virtual instructions. So the browser will download the WebAssembly and then it can compile it down to the target architecture. And WebAssembly, which is also abbreviated Wasm, as I mentioned here, it's a new browser standard, which is very powerful because that makes it so that we as web developers can use it in any type of browser here. And part of the reason why WebAssembly was so quickly out on the market was that it's based on on a previous project called asm.js. So if you're interested in the history, I recommend you to have a look a little bit more into that. And WebAssembly is an intermediate language, so similar to in Java, you have bytecode, and in C# you have the MSIL language. And it's strongly typed with 4 different types. You have 32-bit integers, 64-bit integers, 32-bit floats, and 64-bit floats. So now we'll have a first look here at the hello Wasm example here. And in most programming languages, when you write a hello world example, then you actually print out the hello world text. But now, as you saw here before, we don't have any string representation, so it's actually quite tedious to do a hello world example in Wasm. So what people usually do instead is that they make a simple addition or multiplication or mathematical operation here. So that's what we're going to do here for our first Wasm example here. So we're using a format here called WAT, which stands for WebAssembly text format. And in this format, we define a module and a function that we call add2, and then we define the input parameters. So in this case, we want to have 2 32-bit integers as input parameters, and then as a result, we want to have 1 32-bit integer out. And WebAssembly is a stack-based language, so you can push and pop onto the stack. So first we get local 0 and we get local 1. So we get what is on the stack, and then we use an already built-in function in WebAssembly, which is the add function. So there are some 70 different functions that we can use. And then after that, we need to define what do we want. If we have a calling program, what will this calling program use in order to call this function? So then we need to export add2 as a module and also this function name add2. And here's actually, we can have a look at what this looks like. So there's a tool here called what2wasm, where we can actually see what would this look like, WebAssembly code. And as you can see here, it's very similar to assembly language here. So maybe you can see some parts in this code where they do actually the i32 add operation and so on. But then in order for us to use this, then we can create a simple HTML page. And then what we do is we do fetch on this add.wasm, which is a binary file. And then after that, we read it into an array buffer. And then since WebAssembly is a standard, we can just call WebAssembly.instantiate with this byte array that we just read in. And then we can define that we want to use this add2 module, and then we can just do an alert add2 and then put in some integers. And then we will have a WebAssembly result in our web browser. So that's a simple example here on how we can use WebAssembly here. And then there's also a tool here called Wasm Code Explorer. So that is if you already have a WebAssembly and you want to see what is the textual format of this WebAssembly binary format, then you can use the Wasm Code Explorer, and then you can load your Wasm into that, and then you will get a textual representation, as you can see here on the right-hand side. But as I said here, we don't really want to be writing WebAssembly by hand. So instead, what we would like to do in order to be more productive is we want to use a high-level language, and then we want to be able to compile this high-level language down to WebAssembly. So one of these languages that we can use is called Rust. So now I'm going to give you a quick introduction here to Rust. So Rust is a system programming language from Mozilla, and it has a syntax similar to C or C++. It's strongly typed, and it compiles down to native code. And one of the design criteria when they developed Rust was that it should be memory safe guarantee. And that means that you will not have any memory losses in your program here. And if we want to use Rust in combination with WebAssembly, we need to learn a little bit about the tool chain. So in Rust, we have Rust App, which is an installer for this system program language Rust. And we also have Cargo, which is the package manager. So cargo is very similar to npm. So when we make a package in Rust, we can upload them to the crates.io, which is the package registry for Rust. And then Rust C or Rust compile. So if we have a program here, like a function main, and we print out hello world, then we can use Rust compile to compile this Rust program. And then on the Windows machine, we get an exe file, and then we can just execute the exe file, and we get hello world out on the console. You can also use cargo here. So if we use cargo new hello world, then it will create a folder structure and a hello world project for us. So it will both have a source folder with a main Rust file and a cargo.toml file. So the cargo.toml file is like a package description. So in the toml file, you define a name for your package, a version, and also the author. And you can also define dependencies if you have dependencies on other crates. And then we have the main.rust file where we define our program. So if we want to run this, we can just use cargo run. So what it will do, it will compile our hello world program. And after that, it will also run the exe file that will also be generated. So in Rust, we also have some different types. So we have both primitive types and primitive constructs. So some of the primitive types is both booleans, integer and floats, and chars and strings. And we also have some primitive constructs like arrays and function pointers and references. So now we're going to go through here. So how can we do here if we write the Rust program and then we want to compile it down to Wasm, and then we want to use this Wasm on a web page? How can we do this? So the first step here is to compile our Rust program down to Wasm. So the first thing that we do is we install the Rust toolchain, which I was just talking about, which is this Rust app, cargo, and Rust compiler. And then we need to add a compiler target. And this compiler target is called wasm32 unknown. So that informs our compiler that we want to compile down to WebAssembly. And then after that, we can install something called the Wasm bindgen. So the Wasm bindgen will generate bindings from our JavaScript program to Rust and WebAssembly. And it looks something like this. So first, as similar to our previous example, we have this toml file or the package file. We define a name for our package and the version and the author. And we can also define what kind of library is this. So in this case, we call it a cdylib, which is the format for the Wasm. And then we define some dependencies. Like here, we says that we need to have it depending on this Wasm bindgen, so in order for us to be able to call our WebAssembly from our JavaScript application. Then we have our Rust program. So in this program here, we first define that we are dependent here on the Wasm bindgen. So we do that by using extern crate, and then we define which is this crate that we are depending upon. And then after that, we can mark up here that we want to be able to use an external function here. So the external function is the regular JavaScript alert function. And then after that, we can use Rust, and we just define a greet function, and that we have a string as input, and then we use the regular JavaScript function, and we format hello, and then the name that we had as an input parameter here. And after that, we can use a tool, Wasm pack init, in order to package our example here into a package that we can then publish as an npm package. So you can see here there are 4 different files. It's the Wasm file, and then it's a TypeScript file and the JavaScript file, and also a package.json file. And then we can just use npm publish as with any other npm package, and we can publish our package up to npm. And then we can see here on npm we got this hello Wasm silver package. So now we will have a quick look here also what what does these 4 different files, what do they contain? So the first file was this TypeScript file. So in the TypeScript file, we get the listing here of the functions that we can call in our WebAssembly. So we have this greet function that we would like to be able to call. And then we have the hello wasm silver.js. So this is this glue file that I was talking about before here, so that you can actually call from your JavaScript application down to the WebAssembly. So if I have a quick look at what it says here, it says it tries to pass a string down to the WebAssembly, and then it returns WebAssembly.greet, which is this function that we were using. And then finally it frees up the memory for us. And then we have the package.json file, which is a regular package JSON. So if we want to use this, we can create a webpack config. And in this, we just define an entry for our web application. And then we have a package.json where we say that we need to depend on our hello wasm silver npm package. Then we can create, as we did before, we can create an index.html file. And in this index, we just refer to an index.js file. And in the index.js file, we import our hello wasm silver package. And then asynchronously, we can load this and run this js.greet function with some inputs. So if we run this in the browser, we get on the alert here, we get the hello and then the input that we entered. So these were, I'm just going to take a little bit here to drink. So these were some simple examples here on how we can use a high-level language and then compile it down to WebAssembly. But now we're going to have a quick look here at a little bit more complex example here, which is the game of life. So, so just a review here. So the game of life is a simulation. So you simulate some cells that can reproduce. So if you have, so there are some rules to these games. So if you have a live cell with fewer than 2 live neighbors, it will die because it will be underpopulated. And if you have a live cell with 2 or 3 live neighbors, it will live on to the next generation in the simulation. And if you have a live cell with more than 3 live neighbors, it will die because it will be overpopulated. And then it's also, if you have any dead cell with exactly 3 live neighbors, it will become a live cell because of reproduction. And this is also an example that you can have a look at from the Wasm's official pages here. But if we have a look at what this looks like, and then we can run this simulation. So now we can see it simulates this different cells, and then we can also, we made an event handler, so now I push on the pause button like this, and then I can manually go in and add some cells. So I added some cells in the middle, and then we continue with our simulation. So let's have how we got some more interactivity into our Wasm. So the way that we did this was we have the toml file, cargo.toml, which looks similar to what it looks before. We have a dependency on this wasm bindgen so that we can call it from a JavaScript application. And then over here we have a library.rust file. And in this Rust file, we define this universe, or the simulation game plan. So we define how many cells should it be, like the width and the height. And we also define some getters and some setters for the width and the height. And as you can see here down to the right, we define the toggle cell function. So with the toggle cell function, that's where we can add this interactivity so that we can go in and manually check a cell here. And then it's also similar to what we had before here. We have a TypeScript file, and in this TypeScript file, we define all the different functions that we can call from the outside. So for example, we can call this universe that we were looking at, and we can call render and the width and the height, and we can also call this toggle cell function. And then we have this JavaScript file, which is this glue file. So similar to what we have had in the previous examples. So here, for example, when we get the width, it tries to return wasm.universe_width with a pointer. And for example, with the toggle cell, it tries to call this wasm.universe and then toggle cell, and then the argument, which is the X and the Y coordinate in the simulation. And then we have here our index.html file, and we're defining here a bootstrap.js file, and then the bootstrap.js file, we are importing an index file here. So this is our index.js file where we import the universe, and then we add some event listeners, and then, for example, you can see a little bit further down below, we call this universe.toggle cell with a row and a column. So now, as I mentioned here, one of the criteria here with Wasm is that it's binary and it should be very, very performant. So let's have a quick look here at what that can look like. So there are some people that have made some investigations here. So you can see here on the y-axis you have the time in milliseconds, and then you have either JavaScript or WebAssembly in 3 different browsers. So we start out with Chrome, and then we have Firefox in the middle, and then to the right we have Safari. And then you can see in this box, in the box plot, we can see that the JavaScript is usually much slower than what the WebAssembly is. But maybe what is more important here is that there is a much more spread among the values here. So what that means in practice is that when you run JavaScript, you can see that there's a quite a big spread between the performance, for example, in Firefox. But whereas if you look at the WebAssembly, you can see that the spread is much, much lower, which means that we can count on the WebAssembly performance, that it will be very, very similar when we run it another time. But we should also take into account here that JavaScript has been around for quite a long time, therefore the browser and the JavaScript engine has been optimized for performance. Whereas that's not really the case here with WebAssembly. WebAssembly is a much newer player in this field, so we can count on with time that it will be more optimized, and that these time differences will be even larger, that WebAssembly will be much faster here than JavaScript. So now I'm going to go through some real-world examples here. So one of the use cases here for WebAssembly is actually if you already have an application which is written in, let's say, C or C++, and you want to expose this for a larger audience on the web, then WebAssembly is a great use case for this, because then you can compile down your application to WebAssembly, and then you can write a wrapper in JavaScript, and then you can make a web application out of it. So that's one good example of how we can use WebAssembly. And this is an example of a digital signal processing library, which was written in C, and then they compiled this down to WebAssembly, and then they could expose this DSP library on the web. So if you want to have a look more, there is a GitHub library on this link here, and then if we run this, then it would be looking like this. So this is both for videos and for images. So here we can do image manipulation in real time, and we can choose some different types of manipulations here on the left-hand menu. So all of this has been implemented in C, but then we have compiled it down to WebAssembly, and then we can call it in, we can use it then on the web. Then another example is from AutoCAD. So AutoCAD, they have been in the business for a very long time, and what they do is they specialize on drawings. So just for some history here, so AutoCAD in 2010, Flash was sort of the latest technical advancement. So what they did is they used a Flash application in order to be able to view these AutoCAD drawings on the web. And then if we fast forward to 2014 or 2015, then it was the HTML5 and JavaScript, which was the greatest technologies. Then they used that in order to build a viewer for the drawings that you could view on the web. And then in 2016, they used another compiler, Emscripten, and then they could compile this down to Emscripten with that. And then in 2017, in AutoCAD, they have a format called DWG, so they made a real WG-based viewer. And now in 2018, they had a web app launched, which is using WebAssembly for that. And if we have a look at how they structure their application, they are still using the same C++ code as they've had in their previous generations of their product. But what they did is they made a small layer here in WebAssembly so that this WebAssembly could call down to the C++ code, and then you could call from your web application, you could call from JavaScript code down through WebAssembly down to the AutoCAD core code. And I think this is also a good example of differentiation of responsibilities here, that you have 3 different layers and you can have different developers working on the different layers. So this means that they could still keep their expertise in the AutoCAD core functionality, and then they could have other developers work on generating a good front end for their web application. I'm going to say a couple of words here about some future plans for WebAssembly. So maybe you've noticed here that I've been talking about this glue code that we get here from the Wasm bindgen. So the glue code is a code which sits in between the JavaScript application and the WebAssembly. And what's next in plan is they would like to be able to get rid of this glue code so that we could actually call WebAssembly directly from the DOM or from a web API. And you could also see here that when we were using WebAssembly, we always needed to go through like a bootstrap.js or an index.js file that we were loading asynchronously. But they also would like to get rid of that and instead have like a direct import of Wasm in JavaScript, like other NPM packages or other packages. And they would also like to be able to support more languages. So I should say also that right now it is only working here with languages that doesn't have garbage collectors. So for example, Java and C#, they have a garbage collector, but we can't use that in Wasm as of now. But another interesting thing that you can use WebAssembly for is something that you can call serverless WebAssembly. So WebAssembly is not only for the browser. So there are different providers like Cloudflare and Fastly. They support this serverless WebAssembly. And what it leads to both fast launch time. You don't need to rewrite to JavaScript, and you can have more lightweight applications. So an example of how this could look like is this here. So let's imagine that you have some data processing modules. So either you can have this running on the server side, so you just have a regular front end, and then you have the data processing on the backend side. Or you can have everything on the front end, so you have some client-side JavaScript, or you can run it as a client-side WebAssembly. So then you compile, maybe you have your data processing as a C library, so then you just compile your C library down to WebAssembly, and then you can use it in the front end. Or you can compile your C library to WebAssembly, and then you can use it as a serverless function, also using WebAssembly. So that is what we call serverless WebAssembly. Then there are also been discussions here about something called WASI, or WebAssembly System Interface. So here the idea is that we will have WebAssembly which actually runs outside of the browser, and we can also think about this as a WebAssembly is a language for a conceptual machine. But then we need to have some sort of an interface for a conceptual operating system. And the idea here is that this should be run on all types of operating systems. So this is also an example here from Lynn Clark here. So usually what happens is if you have an application and it wants to operate on your hard drive, for example, you need to have some sort of negotiation, and then you can call something which is called POST function, which can go directly down to your operating system and execute functions. So the idea here is we have some sort of mediator that the WebAssembly can call, and he can ask the mediator to approve him in order to be able to execute and read and write functions on the operating system. So that has actually been implemented here. So if you want to know more, you can go and look up the Wasm, the WebAssembly system interface. So we're going to have a quick look at how this could look like. So in this example here, we have a WebAssembly module where we want to write something down to disk and then return it out on the console. So what we can do here is we can use a special runtime, which is called Wasm time. So Wasm time is specifically developed for this WASI interface. So you can use the Wasm time, and then you can execute this demo.wat file, and then we get hello world. And then you can also compile this WAT file down to the Wasm format. And then we can just execute our Wasm, which is our WebAssembly, in the Wasm time runtime. And what was also interesting here, so what we did here was that we could store something in memory, and then we could read it back, and then we could console out this from the memory. And we could also use, there's also polyfill, so if you want to use this in your web application, that's also possible to do. So now we will have a quick look also at some other frameworks that are using WebAssembly. So one of these frameworks is called Pyodide. So with Pyodide, what you can do here is you can bring the Python runtime to the browser through WebAssembly. And you can also, with that, you can also bring with you some different Python libraries like NumPy or Pandas or Matplotlib. And the beauty of this is instead of using regular Jupyter notebooks, which can be a little bit complicated if you want to share your material with some other developers, you can just upload this on a regular web page and then share your results through that. And there is also some examples on how we can use Matplotlib in order to do some plottings here. So yeah, so what is important here is that now we can make use of all these rich ecosystems that exist in the Python world. So for example, with Pandas and with Matplotlib, and we can use it on the web by using this Iodide and Pyodide functionality. Another example is assembly script. So what assembly script does, it's a subset of TypeScript that you can use. So it will generate a WebAssembly module here. So for example, here we have a rotate function, we have some input and some output. And then what is important here is that we are responsible here for allocating and deallocating of memory. So when we're using this from assembly script, we need to both do the memory allocate for our code, and then we also need to remember to free it up when we're finished with our execution. And then we have also Blazor. So there's been several talks about Blazor, so I'm just going to go through this a little bit faster, but basically you can have Blazor on the server, like you have client events that will be sent back through SignalR, or you can have it run on the client using WebAssembly. So the history behind Blazor is actually Steve Sanderson. He presented this at NDC 2017. And then the Mono team was interested because Mono can be used as a compile target for WebAssembly. So Mono is an open source distribution of the .NET framework. And then around the same time, it's the .NET team that interested in Blazor, and then they sort of collaborated in order to get Blazor out. So basically what you do is you compile your C# code down to .NET assemblies, and then since we can run this Mono framework in WebAssembly, we can also run this .NET WebAssembly is also in WebAssembly in the browser here. So one of the canonical examples here is a counter. You can define a counter function, and then you can just increase the counter here. And the way that this looks like, if you would look in the developer tools, is this. So it's quite interesting here to have, we both have the Blazor app DLL, and then we also have like the MS Core lib DLL and the .NET standard DLL. And at least in the past, we were not really used to see these types of DLL in the browser. So I think this opens up for a lot of new possibilities, and especially for some developers that are not so terribly familiar with the JavaScript development, then this could be a great tool here, because then they can use the same tool, which is Visual Studio, and they can also use the same language as they've been using before, which is C#, and develop a full-fledged web application without having to rely on JavaScript or other similar tools. I'm just going to have something to drink. But this is not exclusive to C#, so if we have some F# developers here amongst us, there's also something called Bolero, where you can use F# in WebAssembly. So I recommend you to have a quick look here at Bolero if you're interested more into that. So now we've come to the chapter here called New Old. So the question is, have we not seen this before? So for those of us who have been around for some time, maybe we remember ActiveX, or maybe we remember Flash, or maybe we remember Silverlight. So what happened with all of these three technologies was that there were many companies that were focusing a lot on these technologies, but then they got a little bit burned because these technologies support just disappeared. And the question is, can the same thing happen here to WebAssembly? But I would say that with WebAssembly, it's a different type of situation, because all of these ActiveX, Flash, and Silverlight, they're very proprietary technologies, whereas WebAssembly is actually W3C standard. So that gives me much more confidence in relying on WebAssembly. So I don't think it will take this route that these three technologies took before. Now I've come to the end here of my presentation. So the question is here, what can we conclude with? Because when maybe a year or a year and a half ago, then you could read a lot of articles about WebAssembly, and they said that JavaScript is dead and that WebAssembly would take over everything. So the question is here, should we go for WebAssembly all the things? Well, I don't really think so. I think that WebAssembly is yet another tool in your toolbox. So it can be really great for some applications, like for example, the applications that we were looking at a little bit here is that if you already have if you already have an application that you have developed in C or C++ and you want to expose this to a wider audience on the web, then WebAssembly is a great tool for that. But we can also see, at least up till now, that there's a lot of tooling that needs to be put into place, because it's not super straightforward to do all of these things. So I think there's a lot of things that can be done in order to simplify for us developers to start working with WebAssembly. So I don't think for those who are working with JavaScript, they don't need to be afraid. I think that JavaScript and WebAssembly are complementary technologies, so they are not overlapping, but they serve different purposes. And then I have also some references here. So so you can have a look at, there is both on Mozilla and on the WebAssembly official pages, there's both developers guide and startups for those of you who would like to get into this field. And also I've also added some links here to Blazor for those of you who are interested more into that. And then finally here, before I finish, I'm just gonna take a little bit more to drink. Yeah, so finally here, before I finish, I would just like to take the opportunity here to talk a little bit about this AI42 school that I was talking about. So AI42 is an online AI school that me and another AI MVP called Eve Pardy started now in January 2021. And the idea here with the AI42 is we would like to give everyone here on the planet the possibility of getting into machine learning, AI, and data science. So the way that we have done this is that we have invited industry experts and recognized speakers, and they will have sessions that we will be streaming 2 times a month on Wednesdays. So what we're doing is we start out with mathematics and statistics and probability theory, and after that we will move gradually into languages like Python, R, and Scala, and also into tools such as Databricks and Power BI. And we'll also look at how can you set up a machine learning pipeline, or more advanced topics like reinforcement learning or explainable AI. We will also have some workshops so that you can put theory into practice. And all of this is for free. So you just need to register here. So if you're interested, I suggest that you can scan our QR code. So you can either see our previous lectures on YouTube, or you can get notified here through Meetup when we announce our next lecture. And you can follow us on Instagram, on Twitter, and on Facebook. And we're also associated with the global AI community. So you will be able to see our sessions also on the global AI community YouTube channel. And we're sponsored by Microsoft, and we also have a graphic design here by Levente Pongor, and our introduction music by Mina Marie. So that is all for me. So if you have any comments or questions, you can always reach me on Twitter, where my name is Agrevlis, or you can send me an email on the following email address. So that I would like to thank you for your attention and your time, and I wish you a continued good NDC London. Thank you so much.